Okay, guys, first thing I was going to do was, oops, is to talk about whoops, sorry, guys, I screwed this up. Should be project two. I'll fix that. But anyway, this is project two description. So I don't know if you guys looked at it, but it's due in what, like a couple of weeks, Saturday morning, next Saturday. Um, Let me just give me 1 second. So project two it's a how do I zoom out of this thing? Well, anyway, it's a layout project, and the idea is that a lot of times as a design engineer, some of the time you're doing layout yourself, and some of the time you're trying to decipher somebody else's layout. And it turns out that like you may not know who was the person that did the layout. There's like a lot of different cells in a design. So what you end up doing is looking at a layout, like something like this, and you're trying to figure out what it does. You create a schematic from it, and you try to simulate it. So what happens in this particular case? Well, in this particular case, this is kind of like a warm-up exercise, and I've already told you guys that this is a NAND gate, and sort of you see the locations of the inputs and the output. Okay, and then there's like a map here of the different layers, etc. I simplified the layers so I don't have to really look at the end select and so on. So that this is an MOS here. So to me, this looks like one gate. Okay, so this is poly. This sort of a pink look is poly, and it's going over active. So this is one gate going to this input, and this is the next gate going to this input. Okay, and they're in series. So this is the source of one, the drain of the first one, and the same as the source of one and drain of the other one. So if I was going to draw this as a schematic, they would look like two MOSFETs in series. Okay, and then one would have B as an input, and the other one would have as A as an input. And the source of, so let's call this M1, let's call this M2. So this would be M1 and M2. And the source of M1 is connected to ground, okay, which is connected to the substrate. And the drain of M2 is connected to this metal 2 line. It's also connected to the output, and it's connected to these PMOSFETs. So this is out. And the PMOSFETs looks like here's one PMOSFET. So again, this is poly. Anytime poly goes over active, it's a gate. So poly going over active, gate. So so these two look to me like they're in parallel because this is the source of one of them and the source of the other, and these are the drains that are shared. So it looks like, so this is, let's call this M3, let's call this M4. M3 goes to B, the gate goes to B, M3, the gate goes to B. And the source goes to VDD here for both of the devices. So both M4 and M3 have their sources going to VDD, and this guy's gate goes through poly, gets connected to A. Okay, and their shared output gets connected to the output. Okay, so now let's see. I'm trying to eyeball, like in an actual, if you had a CAD tool or whatever, you would be. Everybody with me so far, by the way? What I'm kind of reading this layout, or it's going back.
It's making sense.
Okay. And so the other thing we're doing is, again, you'd be able to measure this in your CAD tool, but in this case, we still don't have our CAD tool. So basically you're like eyeballing this. So I said, use this as a reference, use these lengths as a reference. Oops, why isn't it drawing anything? It's because I'm, so basically this size is 180 nanometers. Okay. So, I mean, this is the important part about this project. So don't spend a whole lot of time trying to figure out what this is to the nth order. I'm just like eyeballing it, and that, I don't know, looks like maybe it's 5 times, 7 times the length, sort of this distance compared to that distance. Let's call it 5 times the length. So the width ends up being, so this is the length, width ends up being 5 times 180 nanometers. Okay, so that was this guy. Length is 180 nanometer, and the width is, oops, trying to calculate what that is. Ends up being 900 nanometers. Okay, so unless you're suffering from OCD and you needed to do it for your own peace of mind, you don't need to like really sweat like what that is. I'm just sort of looking to, I'm assuming, so because then if you had a CAD tool, you just drop a ruler on it, you'd be able to do it. There's no reason to put a lot of work there. Okay, so basically, and then this guy is the same size as that guy, so this width is 900 and length is 180. Okay, and now let's see, I want to eyeball, when you get into the SPICE model, you'll notice that you have area of drain, area of source. These are additional transistor parameters. If you click on the transistor, area drain, area source, perimeter of drain, perimeter of source. Okay, so if you're looking at sort of the drain area in this case, so let me again, okay, let me erase this here. So I said this guy is the drain that's shared by these two transistors. So it's like this, it is this area here, this drain, shared by these two. So that, what I would do is come up with a perimeter, which is around this, you guys can't see it probably. The perimeter is like, around, you guys can't see it, can you? Where I'm pointing to, shoot. Is there a pointer in this thing? No, I don't know. That didn't seem like it was it. Okay. So this is the perimeter. That didn't help. Sorry, guys. Colors, text, magnifier, pointer. No, that's sorry, guys. Is there a draw with finger pencil setting? It's funny. No. Raise. So this is the perimeter. of the drain. So basically, I have to figure out what distance that is. Again, I'm eyeballing it here. This separation is about 4 times 180. So the perimeter of drain is 4 times 180 nanometer times 2. So it's that guy plus that guy. So the rectangle plus the 2 widths. So 5 times 180 times 2. Okay, so that's the perimeter. Do you guys see what I did? So this rectangle here, this rectangle, 2 sides are the same as the width of the transistors, and 2 sides are the separation between the 2 gates. Okay, so this is the separation between the 2 gates, and this is the width of the transistor. So that gives you the perimeter, and because you're sharing it between M3 and M4, you might want to like drop half of it into the model for one and the other half into the other model. And then this is the area of the drain. And that's, area drain is 4 times 180 nanometers times 5 times 180 nanometers. Again, I'm just taking these 2 dimensions and just now I'm doing the area. And I would divide that by the 2 transistors. So now you have the sort of the parasitics, which we're about to talk about. But anyway, I just wanted to point that out. And what else do I want to say? Yeah, just be careful here. From what my experience is, remember this area drain, area source is 2 numbers with 10 to the minus 10 to the minus 6 meters in dimension. So it's 10 to the minus 6 times 10 to the minus 6. What the heck? So area drain, area source in your SPICE stack, it should be 10 to the minus 12-ish. Remember, multiply the dimensions together. Like if it's 10 to the minus 6, that means you're going to get like a huge device. So just remember, it's going to be like something times 10 to the minus 6 times something else times 10 to the minus 6. So it should be a 10 to the minus 12. Whereas perimeter drain, period source are more going to be 10 to the minus 6 kind of distances, a fraction of a micron or several microns. Does that make sense? So watch out for this, because that tends to happen as you put in the wrong dimension, sort of like the wrong. You don't include this stuff in your dimensional calculations. You got to remember that SPICE wants you to input stuff in sort of meters. Okay, in this area drain, area source. Okay, and then finally you do basically once you've extracted this, you'll do a sort of a FF04 simulation. And the way I would do it is, it doesn't matter what you tie this input to. You could either tie it to ground or VDD. Okay, but you want to basically drive 4 other guys like yourself. And you want to basically, by having 2 pulses, 2 pulse trains, one twice so this is A, this is B. It doesn't matter which is which. If one is twice the speed of the other one, then basically you get all so this would be a 1, 1, 1. This will be 1, 0. This will be 0, 1. And this will be 0, 0. And for each one of these, you can see what the output is and prove that it's a NAND gate from input to output. And then you can also, calculate the delays for each case. I didn't put that in, but you want to get the delay for each case. So delay, I'll put that in the, put a note myself. To delay for each case. So depending on what this combination is, depending on these permutations, you might have different rise fall times and prop delays, etc. Okay. So any questions about that? So the reason this is called a warm-up is because I tell you what the circuit is. The next one, you do exactly the same thing, but I don't tell you what the circuit is. I just tell you where the inputs and the output are. Okay, and you're supposed to extract it. But this is still a simple case. And then this is the, whoops, man, I really screwed this up. Sorry, guys. It should be 3. So the third one is the sort of the nightmarish case where, more complicated with like a bunch of transistors now. So here you have 1, 2, 3, 4, 5, 6, 7 NMOS transistors and 7 PMOS transistors, and you're supposed to kind of like decipher what functionality this is. Okay, so this is a more difficult case, but you do the same thing for them over and over again. So anyway, I'll clean up this project 2 description and put it up again, but the gist of it remains the same, which is you guys are reading a layout, creating a schematic from the layout, throwing in some of the parasitics, in this case, area drain, area source, perimeter drain, perimeter source, and simulating with it. By the way, notice that one thing is you guys don't need to worry about, only worry about the perimeter and source of nodes that are not connected to supplies. Like this guy here is just, it'll have some capacitance, but it's connected to the power supply. So there's no change in voltage across that capacitance. So it's not going to affect your delay in any way at all. So, you don't need to worry about it. You only need to worry about these parasitics that are not connected to these supplies. So here you don't need to worry about this. Here you don't need to worry about this, just because those guys are all at DC voltage, they're not going to change. Okay. Any questions? Okay. All right, guys. So, and then I is due like on, I think on the 13th at, this is 13th is a Saturday at the funny time of 7 a.m. just because, that's sort of roughly when I'm going to start grading. And that's it. Okay. If you have any questions, just let me know. And now we can jump in to our, let's see. Let's see, where are we? There we go. Where are we at? We kind of already covered this. Okay, I think we were right here. So basically what we did last time was that we looked at the IV curve of an NMOS, IV curves of an NMOS transistor. And we created a level 1 model. So like a simplest That's what it means by level 1. So, and basically this is how it looked. So the drain current looked like the following. It just looked like 0 if the gate source voltage was less than the threshold voltage. Okay, is equal to beta times VGS minus VT minus VDS over 2 times VDS. If VGS was greater than V sub t and VDS was less than or equal to VGS minus VT. And this beta was Cox W over L mu 0. Oh, sorry, mu n. The mobility of the n-type, mobility of the electrons times the oxide capacitance times width over length. Okay, that's the definition of our beta. Okay, and I sub d is beta over 2 VGS minus VT squared if VGS is larger than VT and VDS is larger than VGS minus VT. Okay. So what does this look like if, you know, we have, looks like we have two, so V sub t and beta are constants essentially for this particular transistor, right? So V sub t and beta are constants. So then the two other things, the variables we have, so, sorry guys. So V sub t is a constant and beta is a constant for this device, for certain W over L ratio, okay? So these are the constants, and the variables are the drain source voltage and the gate source voltage. I have two voltage variables. And, you know, we could create one graph of current versus both the drain source voltage and the gate source voltage if we had, you know, if we wanted to draw a three-dimensional graph. But because on paper we're dealing with two-dimensional graphs, we basically can draw two-dimensional graphs. So one is V drain source and versus I sub D, and the other one is I sub D versus V gate source. And so for this, because we're sweeping drain source voltage, we have to hold VGS constant for each curve. That means we're going to like have a bunch of curves. I'm drawing these badly. So we're going to have a bunch of curves. These are curves of IDS versus VDS, each one for a different VGS. Okay, so because we're drawing a sort of a three-dimensional thing and a two-dimensional graph, so we have to hold, for each one of these curves, we have to hold gate source constant, okay? And so, you know, this, sorry, this should be 2, this should be 1. And so the features of this graph are when VGS is, if I was going to draw a, let's see, let's be orange, it'd be VGS is less than V sub t. If the gate source voltage is less than VT, then I sub D is 0 regardless of what VDS does. It just stays 0. Okay, so that's that curve, which represents this. As soon as my VGS gets larger than VT, then I have these curves, and these curves have two components. One of them is when VDS is less than VGS minus VT for that particular VGS. So in this case, VDS is less than VGS minus VT, so like sort of maybe might be around here. For anything like this, we have this so-called linear, this is called the linear region. As you can tell, it's not quite linear with VDS because we have this VDS term and then we have this VDS term that multiplies by all these guys. So it's kind of a pretty non-linear region, haha. But it's called a linear region because it's, you know, the transistor is acting kind of like a crappy resistor when you change the voltage VDS in that resistor. Whoops. So in this linear region, looks like you have a resistor of this value. You have a resistor of this value as you modify VDS. Okay, it's like a nonlinear resistor. So that would be this part. And then once VDS goes larger than V gate source minus VT, and it might be in this particular curve, it's here. Once you get past that point, there's no dependency on VDS at all. So again, you get a straight line with VDS. IDS with VDS stays constant, like a straight line. And it's basically, it's the equation for it. So here it looks like the transistor looks like so this is in the linear case. In the saturated case, the transistor looks like a current source. That's a function of VGS only. Okay. And that means that if I change my VGS, my IDS is going to increase in a square law way. So this current goes up very quickly with VGS because we have the square law behavior. So I drew it kind of funny. These are not like linear changes in voltage. It would be, if it was linear changes in voltage, the curves would look like kind of like this. They would look like this. So that would be VGS1. VGS2 would look like that. And VGS3 would look like that. So if, let's say if each one of these was like 500 millivolts away from each other or something like that, because we got this square law behavior. Okay. And notice that the point where we're changing from linear to saturation is changing for each one because each one has a different, let me just erase this because I was trying to make a point there, but it gets confusing. So for each one of these, oops, for each one of these curves, the point where VDS is less than VGS minus VT changes because VGS is different. This VGS is higher than this VGS. So VGS minus VT is a lot closer to the origin for this lower VGS than it is for this higher VGS. It's higher over here. So you get these curves that are shifting. And so these are like the actual curves. Kind of erase this for, you can see what's going on here where, you know, this break even. So this is like the linear region, this is saturation, linear saturation, linear saturation, linear saturation. And that point is moving further and further away from the origin because your VGS is increasing. Okay, and this is VDS and this is ID. Okay, so this is remember how we came up with this? We did a real, like a very first level model of what the charge will look like in the channel and the velocity and all that stuff. So it's really a first level model of the device, how it might work. But I still use it all the time, just for back of the envelope calculations. What else do I want to say about this? Okay, I think that's all. And then we said that the PMOS, everything is the same in the same sense that there is, by the way, this is called cutoff. This is cutoff. It's linear and saturated. So in the sense that there is a cutoff, a linear, and a saturation, but because the currents are going in a sort of being defined as coming out of the device as opposed to going into the device, and the device is flipped sort of upside down when you compare it to an NMOS, now the source is hooked up to the supply voltage and the drain is lower than the source. It just looks like a flipped upside down version of the NMOS curve. Okay. And the other thing is, remember that all of these gets multiplied by beta, which you can think of as, sort of a gain term. And beta is, for an n-type, is mu sub n Cox W of n L sub n. So this is for a transistor. You can change the design of the transistor by just drawing it this width over length ratio differently, but you can't change the mobility of the Cox for a particular process. And then beta P is the same as the mobility of the holes. Cox is the same, and WP over LP. So this is the sizing of your P MOSFET. Now, it turns out that in silicon, all things being, no second order effects, the mobility of holes is about 2-3 times smaller than mobility of electrons. Okay. Mobility of holes is 2-3 times smaller than mobility of electrons. So in this class, we just assume when we're doing first level calculations that there's about a ratio of 2 between the holes and the electrons. Okay, so what does that mean? That means if you wanted to have a PMOS that's sourcing, let's call this ID, sourcing the same value as how much a NMOS sinks. Okay, if this W was WN, you got to make this W 2 times WN for the IDs to be equal to each other. Okay, because that way the beta sub P will look like twice. You need to make up for this mobility difference. Everybody with me? Anybody confused so far? No? Okay, so this was the first level equation of the currents coming out of NMOS and PMOSFETs. And remember that we said that the two key things were current and capacitance, because if you look at the delays, okay, so Q is equal to CV, so dQ dt is C dV dt, okay? So there's a change in voltage with change in time kind of tells you, if you have, whatever, an inverter, how fast you're rising and falling, right? Just change in voltage with time. Those are all sort of the delay. And this is current, as the change in current with change of time. So if you look at delta V over delta T is current over capacitance. Okay, so we just saw what the current looks like. Now let's look at the capacitances of these devices. Okay, which is the sort of the other half of the speed equation. So again, these are the current equations, and now we're talking about the capacitance equations. Okay, so if you look at a MOS transistor, so this is the silicon dioxide, this is the gate, this is the source, this is the drain. Okay, so you can roughly divide this into capacitances that are required for the operation of the device and capacitances that are just parasitic. And parasitic means they're kind of useless. They're just sucking up. This is not useful, so you just want to reduce them. But so the gate capacitance is, if you remember, the gate capacitance is what creates this inversion type of this channel for the gate. So if that capacitance went away, the device would never turn on. So you can think of the gate to channel capacitance as being a necessary part of this device operating, okay? Meaning that if you want the device operating a certain way, you just have to give it a certain width and length, okay? Because that width and length decides how much current will flow through the device. When you're building a logic device, typically you'd never want to make the length any longer than the minimum length, okay? Because it's just going to hurt you. There's no benefit. So if you want the device to pump out more current, you basically end up increasing the width. And that increases the gate capacitance. So it makes the device difficult to drive for the previous stage, which is pumping current into its gate. But you just have to do it. That's just the penalty you have to take. You don't have any choice. Okay, so that's a required capacitance. The source and the drain also have a certain capacitance, as you know, we're going to get into it. You're going to see in your project too. And this is the capacitance of, these look like diodes, right? This is N plus into a P. So it looks like a diode. This looks like a diode to this device. And this capacitance isn't really, if you can minimize this capacitance as much as possible, that's what you'd like to do, right? It's just this thing that you're forced to have because ultimately you need to connect to the source and the drain some of the time. And so you need that to be, but if you somehow magically, if you could make those really, really tiny, you would make them as small as possible. So this is the source and drain capacitance or the parasitic capacitance, and you want them to be as small as possible. Okay. So let's look at the gate capacitance for first. Okay, so we basically said the gate, we call this epsilon, this epsilon aux over T aux. We call that C aux, just to make life easy for us. And the reason for that was because as designers, we have no control. So as designer, we're stuck with C aux value. So there's no reason to continue doing this. Oops. Hey guys, do you guys still see my screen? Guys?
Yeah.
Yeah.
But I am not updating. I think it's frozen. Let me try what happened. Yeah, I'm going up and down and it's not changing. What do I do? What does it want me to do? Let me just change the sharing. Yeah. Okay, let me try to restart sharing here. Oops. So let's see. Okay, good. We're back on here. Okay. So anyway, so the Seox, we have no control over it. We just sort of make it one number, Seox. But W and L is what you as a designer are sizing these transistors at. So W times L times Cox gives you your gate to sort of substrate capacitance. Okay, so this is the tricky part that, again, it's easy. Like you only do this in digital design, okay? Is like I said, you never in digital design use minimum L. Okay, you never, this is the length of this device. In digital design for CMOS, standard static gates, there is, you're only hurting yourself for making this longer than minimum length. If you make it longer to get the same low resistance, you need to make this wider and you're just increasing your gate capacitance and there's no winning. So I want to make this the minimum length, okay? So if you do that, then the Cox times L combination also stays constant and you get this capacitance per micron of width. So basically notice this capacitance that's given as this example is per linear dimension, it's not per area. Okay, so this is 2 femtofarads per micron, means that if I have a minimum length device, I just think, okay, well, my device is 10 microns wide, and I end up with 20 femtofarads of capacitance. These are all just simplifying things you do to make calculations easy for yourself, okay? But just watch out for this. Watch out for this because like sometimes I've noticed is one common mistake that people do is they actually calculate the area and multiply it by this 2 femtofarads per micron, not realizing this is a capacitance per micron of width, assuming that you're using a minimum length device. Any questions about that? Oops. Okay. All right. Okay. So that was the gate. So like in our project 2, you should have, I guess, I don't know if you were looking at the layouts, but again, all the gates were minimum length. And then they might have had different widths. Okay. And this width and length, when you put it into your SPICE model, it calculates your gate substrate capacitance. Or if you were going to do it by hand, you would just multiply the width by whatever is this number, okay, for the particular process. Okay, so that's the gate capacitance. Now back to the drain source capacitance, okay? Remember we said the drain source capacitance is just a parasitic. We don't want it. And so we want to minimize it where we can. There's almost no place, again, in digital design where higher capacitance is better. In analog design, most of the time, higher capacitance is better, but not from a speed performance. It's from a noise perspective and accuracy perspective. But anyway, digital design is different. Capacitance is just plain bad for the most part. So we want to basically lay out our transistors or do whatever we can to reduce these drain source capacitances as much as possible. And really, this comes down to a few options, okay? So these are the options. So you cannot, the process has told you that, so this is sort of a typical drain or a typical source or vice versa. Drain, source, drain, source. Okay, so the process has told you, hey, you need to contact this. I got a minimum size contact. Okay, well, so that's the minimum. And then they tell you, oh, we've got a minimum overlap of the active needs to overlap the contact by a minimum amount. So now you're stuck to this dimension. Okay, and then they tell you another rule that the contact has to be away from your gate by a certain distance. So basically, you're kind of stuck with this size as your minimum size, okay? So, okay, I can't do anything about that. But one thing you could do, if you notice you have a series type of situation, because note that, so this is the, say, bottom half of a NAND gate, like we have in our project one, so the first problem. We don't need to make a contact to this point, okay? And these two are in series, meaning that we can actually share this guy across two devices, and we can even shrink it further because we can get rid of this contact and get rid of this contact to gate separation rule. Okay, so we can get rid of this distance, and we can get rid of this distance and this distance and end up with the rule that says this is the minimum separation between two gates. Okay, so we went from this plus this being the capacitance of this node, this plus this, to this, which is roughly half of this, okay, to getting rid of this contact because we don't need to contact to it, to just this. Okay, so basically that's one popular layout technique to reduce these parasitic capacitances. When you see two transistors in series, you basically merge their drain sources together and get rid of the contact, and you minimize the capacitance there. Now notice I wasn't able to do anything about this node, okay, because that node goes to your PMOS transistor, so I can't merge the drain and source of a NMOS. Sorry, I can't merge the drain of an NMOS with the drain of a PMOS because one of them is N plus, the other one's P plus, so I can't do that. And this side, it doesn't matter anyway because it's, it's grounded in this particular case. So I don't care what the capacitance is. But even if I did, again, that I need to connect this to ground or to the body contact for the NMOS, which is P plus. And again, I can't merge those. So anyway, this is like a particularly popular method of reducing the capacitance of series devices. Okay, and then there's another method, which I don't seem to have a slide for, so I'll try to draw it for you guys. So now let's say if you had two parallel devices, like I do with a PMOSFETs of a NAND gate pull up, or I have with the NMOSFETs of a NOR pull down. Okay, they're parallel devices. What I can do is I can merge one of these points. Okay, and this is what I can do. I can basically draw them like this, and then I have two gates. Okay, I still need to contact. I need to contact both sides, right? Because notice I got a contact here and I got a contact here. So I can't get rid of the contacts, but at least so it's kind of like I've gone from here to here, but I can't take this step because I need to have a connection to this node. So it's not as efficient, the parallel reduction, as the series. The series is very efficient. We're doing two-step reduction. We're just doing one-step reduction. And then I have a choice now. I can either make these, so I'd have to connect this and this with metal one. And then this is another one. Okay. Everybody see what I'm doing? So this is unmerged, but I'm connecting it with metal. So it could be either this or that. And this is actually merged. So I help myself a little bit. Now I have because the transistors are symmetric, I can make this the drain and this the source. Okay, so I can make this node, this node. So let me just redraw this thing. So in the case of PMOS NAND gates, these would be their drains, and this would be the sources. So either I can make this merged node, or this and this merged node, or vice versa. I could make this the drains and this the source. Okay. And in that case, notice that I have reduced the capacitance of this node, but I haven't reduced the capacitance of this node, right? This node has higher capacitance than this node because the periphery is bigger, the area is bigger than the periphery and area of this node. And so if I connect this to VDD, it's preferred because this node has a higher capacitance than, so what do I call it? Diffusion capacitance high. This will be diffusion capacitance low. So this is the node that's connected to the output that goes up and down in voltage. So I can reduce this. Salvador, you told me a while back, sorry, you said, can I repeat what you said? Your mic cut out. Do you remember by any chance what I was saying at that point? Sorry, I just saw your note. For the gate capacitance, do you remember that? Well, you know what, that you were saying something about a special case. Shoot, can't quite remember. So let me just give you the key parts of the gate capacitance. Rewind on that. Hopefully that will catch whatever you missed. Basically, the gate capacitance, you gotta have it, right? You can't, if you want a certain output current, you cannot make this any smaller. You just use minimum length. And if you want more current, you have to increase the width. Okay. There's no reason to make this longer than minimum length in a digital design. Okay, so basically for a certain current, you have a certain capacitance. Okay, in addition to that, because we have no control over the thickness of the oxide, the dielectric constant of the silicon, and we're keeping L constant, we can just come up with a capacitance per unit micron of width. Yeah, that's okay. Thanks, Ruben. So it's basically that. So make sure when you see something like this, 2 femtofarads per micron, it's talking about a minimum length device, and you just multiply this by the width of your device. Don't multiply it by the area of your gate. Multiply it by only by the width of the gate, because it's assuming that your length is minimum length. Because for almost 100% of cases, there's no reason to make a transistor longer than minimum length in a digital design. Okay. Any questions, guys? So this was a level 1 simple model of current and capacitance, and together they sort of make your level 1 model. Okay. Whew. Okay, so now, you sure you don't want to slow me down with some questions, no matter how trivial? Give yourself some breathing room, otherwise I'm just going to keep going. I can keep going all night. Just kidding, guys. But anyway, so let's see. I got to get my slide. Where's slide deck 6? What? I failed. I think slide deck 6, hopefully it's on Blackboard, right? The next one?
Yeah, it is.
It is. I just didn't input it in my note-taking thing. Just give me 1 second to plug it into my little good notes. See, good. That's going to burn some time to let stuff sink in. Did I guys tell you about the Andrew Huberman podcast?
The one that you sent an announcement for?
What's that?
The one that you sent out an announcement for a couple weeks ago?
Maybe, yeah. It's a podcast from this guy who is a neuroscientist at Stanford. Great podcast and great guy, because he's talking about the specifics of how you can improve your performance from a neuroscience perspective. But anyhow, what he was saying is, to increase your retention, what you want to do is have a 90-minute period of extreme focus, and you're going to have to keep honing it. It'll be hard to keep 90 minutes of extreme focus when you first start, but you keep working at it. But it ends up being 90 minutes, followed by some period of time where you're not doing anything. Either you're napping, or you're just doing some, just sort of walking around in nature, or going for a jog, listen to music. You're not thinking. And that combination, you actually sort of do your learning after the 90 minutes in that period of doing nothing. I don't know why I just brought this up. I was just thinking you guys need a little bit of time to sort of chew on this stuff. So anyway, let me lecture slide spring, slide deck 6. Hopefully this is right. And import. Yeah, that guy really makes me want to getting into a little bit into neuroscience. It's an interesting area. Okay, let's your slide next spring. What did I just do? Sorry guys, I should, instead of talking, I should have been focusing on what I was doing. Okay, slide deck 6. Okay. Still working on it, guys, sorry. Okay, is that the right one? Okay, that's the right one. Okay, hopefully this will update. Come on. Okay, let me try to. This is slow to update. Okay, let me do this. Okay, so you guys see my desktop, right? Do you guys see my notes? It says slide deck 6.
Yes.
Okay, great. Thanks, guys. Sorry. Okay, so the previous deck of slides was talking about the level 1 model, which again was like a really simplified model. Now in slide deck 6, now we're going to talk about all the non-idealities that you actually see fairly quickly. So these are, you could think of these as sort of second order effects. There's, third, fourth, fifth, 10th order effects that affect your performance, but these are the second order effects. So we're going to start talking about the non-idealities. And, this was the equation. We went over it. This is like a level 1 model. And so, but if you plot an actual transistors, if you plot the model in a simulation tool, especially for a tighter process. You guys see my cursor? Maybe I should put it up. Let me. Okay. Can you guys see this? Sort of looks like an LED-ish kind of thing. So this is especially for a tighter process. So this is a 65 nanometer process. So if you were going to take the threshold voltage and the beta of the device, and the level 1 model, you'd end up with these curves like we drew. They're the curves in black. And you notice how they go from, they're like widely spaced. So this is a gate source voltage of 0.6, gate source voltage of, 0.4, 0.6, 0.8, 1. You see these are taking very big steps, these black curves, the saturation currents, which shows the square law model. And then it's, also they have this flat response in saturation. They're not changing. Okay, so that's what you would expect with the level 1 model. But as you guys noticed, even in the simulation models we were using for the project, the level 1 model only has like a couple of parameters. It has, mobility, it has COX, and it has the threshold voltage. But as you can see in your splice models, there's like, a lot of numbers there. So there's a lot of non-idealities. So if you actually do a simulation, you'll notice several non-idealities right away, especially in a tighter process, in a smaller process. You might not see it so much in the 180 nanometer process. You'll still see it, but not as drastically. And so the first thing you'll notice is, whereas the ideal model says there's these big steps between gate source values, when you actually simulate real transistors, those steps tend to be a lot smaller. Okay, the blue is the simulation. Okay, and so these steps between 0.4 and 0.6, 0.6 and 0.8, 0.8 and 1 are a lot smaller. Okay, also notice that the actual maximum value of current is lower for the real case. For example, if this is, you guys see my little red cursor?
Yes.
Yep.
This is the gate source voltage maximum current for a gate source voltage of 1 volt. And in this particular case, it gives you 747 milliamp of max current. And then if you use the level 1 model, that same volt would give you, I don't know, like 1300 or I don't know, 1250 milliamps. So the level 1 model is predicting also a significantly higher saturation current. So that's happening. The second thing is our level 1 model said that this part of the curve, the saturation part of the curve, should be flat. And you can sort of pretend the device is a current source, but in reality, there's this sort of a slope, a rising slope with the drain source voltage, even in the saturation area. So those are the major non-idealities we see when the transistor is on compared to a level 1 model. Okay. So again, this is like redrawing the same curve when the device is on. Remember, in a CMOS transistor, a CMOS gate, when the device is on, the gate source voltage and drain source voltage are both going to equal to VDD. Okay, when the device is on, we put a logic 1 on the gate to source, and so it looks like the supply voltage, VDD, and the device is either pulling the device fully to ground or fully up. So anyway, you end up kind of in these regions a lot when the device is on. So in those cases, what happens is your on current ends up being less. Plus, to get there in a transient way, you follow a weirder curve. Okay, so that's one. And then also when your device is off, we initially in this cutoff region, so in the cutoff, we assume that there was absolutely zero current going through the device. But in a real device, you'll actually get some amount of current. It's a small number, but it's still a certain value. So if I was gonna, this is a zoom in or a log kind of plot. In the current is in the log domain, and the gate source voltage is in the linear domain. So this is gate source versus I sub D. This is drain source versus I sub D. Okay, so this curve is for a particular drain source voltage. Remember when we plot V gate source versus IDS versus the current, we have to keep the drain source voltage constant. And when we plot drain source voltage versus ID, we have to keep the gate source voltage is constant, okay, because it's a two-dimensional plot. Anyway, so our model would say that, you have this current versus V sub t, and as soon as you get to the threshold, this current would go to straight to zero, like, I don't know, wherever zero is on this plot. It just go all the way to zero. But what happens is it goes down but once you're below threshold, it goes down, down. And notice it's going down pretty fast because this is the current axis is in the log scale. So it's going down pretty fast, but there's still some. And then even when you get to zero, you're at some current, some off current. And notice it's a pretty small number. In this particular case, for this process, it's 27 nanoamps per micron, okay? And this might be more like hundreds of microamps or milliamps per micron when you're on. So this you can think of being 3 to 6 orders of magnitude lower current than when the device is on. So still a small number, but also remember that one of the things that we're doing to keep our power consumption manageable in a large chip is keep most of the devices off and only have very few devices on. So there might be, just as this is like, 1,000 or 1,000,000 to 1 lower current between an off transistor and an on transistor, but there might be 1,000 to 1,000,000 more transistors that are off than are on, meaning that when your chip is off, you mean like there's no switching happening, that power consumption may be similar to, or maybe like 50% of the power consumption when the chip is operating, okay, which is really bad news for mobile devices, which means that, in a real device, you can't count on just things being off, having low power. So you have to do other kind of things to keep your power low. So those are the two main non-idealities, that when the device is on, you don't get as much current as you'd hope for. And you get there in a weird way, which we'll see how it'll affect things. And when the device is off, you don't get zero current. You'll get some current, some leakage current. Okay, so those are two main ones. Okay, so now let's start looking at let me stop here, guys. And so that was a good, probably a preamble or a sort of like a high level view of the non-idealities we're going to talk about. And then, next lecture, we'll start describing a bunch of these non-idealities and what's the physical mechanism behind the non-ideality and what the equations look like, etc. Any questions? Okay, guys. In that case, I'll let you guys go and have a good night. Talk to you guys on Thursday. Take care.
You too.
Bye.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor. Have a good one.
Thank you. Oops. Sure.